Welcome back, focused learners. Today we are tackling one of the absolutely most fascinating and really foundational concepts powering modern AI. We're going to completely demystify mixture of experts, or MoE for short. Now, if you've been following AI's wild evolution lately, you know that scaling up model parameters is, well, it's the name of the game. And there's a good reason for that, right? Massive scale is exactly what unlocks those magical emergent reasoning capabilities we're seeing in the latest systems. But here's the catch. How on earth do you scale a model up to 1 trillion parameters without needing, like, your own personal nuclear power plant just to run a single query? Well, the physical, real-world solution to that is MoE. Okay, let's dive into this. So here's our roadmap for this explainer. 1. The dense scaling bottleneck. 2. Enter mixture of experts. 3. Under the hood of MoE. 4. Managing traffic and dropping. 5. Scaling to the frontier. And finally, 6. The future of sparse AI.
All right, starting with Section 1, the dense scaling bottleneck, the physical and economic limits of AI.
And this brilliantly illustrates the fundamental wall we hit with traditional architectures. You see, in a standard dense network, every single parameter fires for every single token. It's like when you read a word, your entire brain lights up at once. As you pump up the model size and the data size, you just slam headfirst into memory bandwidth walls. The sheer cost of all those floating point operations, the flops, when multiplying these giant matrices, it creates a massive quadratic blowup of training and inference costs. It literally becomes economically and physically impossible to scale any further. So, the paradigm shift to fix this? Move into sparse networks. Instead of lighting up the whole brain, we use something called conditional computation. This selectively activates only a tiny, highly specialized subset of parameters based exactly on the data it's currently looking at. Which brings us to Section 2. Enter mixture of experts, a true paradigm shift in compute.
Now, you might be surprised, but the core concept here is actually kind of old. It kicked off way back in 1991 with adaptive mixtures of local experts. But the big modern leap? That happened in 2017. That's when Shazer and his colleagues introduced the sparsely gated MoE layer. This was a real game changer because it finally proved you could scale deep learning to massive sizes by dynamically routing tokens to the top experts inside a single network. Then, jumping to 2021, the switch transformer made another huge leap. They simplified the whole architecture. Instead of routing a token to multiple experts, they routed it to just one. This dramatically improved training stability and, get this, allowed them to scale all the way up to 1 trillion parameters. And today, in 2025, models like GPT-4 are pushing these sparsity frontiers to absolute extremes. So yeah, it completely transformed from just this neat academic curiosity into the literal computational backbone of modern AI.
To put it playfully, and I absolutely love how our source material notes this, you can think of MoE as multiple experts, individual models, basically hiding in a trench coat. When you query a frontier model today, it feels like you're talking to this one unified omniscient brain. But under the hood, you're actually talking to a highly coordinated committee of different specialists all working together as one. Let's crack it open. Section 3. Under the hood of MoE, the mechanics of routing. Okay, let's do a quick hands-on exercise here. Imagine a traffic cop standing at a really busy intersection. Step 1. Tokens arrive at the MoE block. Let's say we have a blue token representing a math concept and an orange token representing French grammar. Step 2. Our traffic cop, which is the gate network, looks at these tokens. It evaluates the blue token and dispatches it straight to expert 2, our math specialist. Then it evaluates the orange token and shoots it over to expert 1, the linguistic specialist. Step 3, those specific experts actually process their assigned tokens. Now listen, here is the real magic of this whole system. While experts 1 and 2 are grinding away doing heavy matrix multiplications, experts 3 through 8 are completely dormant. They're just sleeping, drawing essentially zero compute power. Finally, step 4, a ReLU activation function processes those outputs into a final result.
But what happens when an expert gets too popular and everyone wants it? That leads perfectly into Section 4, managing traffic and dropping, keeping the flow moving.
You see, hardware requires absolute predictability. We really can't have one GPU just sitting there completely idle while another one is drowning, overwhelmed by 1 million tokens. So, we define something called expert capacity. This is a strict upper bound on exactly how many tokens an expert can handle per step. The baseline math is simple, just the total tokens divided by the number of experts. But because routing has this inherent randomness to it, we multiply that baseline by a safety buffer.
So the crucial point is this capacity factor, and it's a super delicate trade-off. If you set the capacity factor way too high, you're just wasting incredibly expensive GPU memory on empty buffer space. But if you set it too low, you won't have enough room for sudden traffic spikes, and you're going to end up dropping a bunch of tokens.
And speaking of dropping tokens, what actually happens if an expert hits that absolute capacity limit? Well, the extra tokens overflow, and traditionally they get dropped. This means they just bypass the expert entirely, slipping right through a residual connection and completely miss out on that specialized processing. How do you handle that drop matters immensely. In early MoEs, they just used a random drop policy. I mean, imagine randomly discarding a word that's absolutely crucial to the meaning of a sentence just because a computational queue happened to be full. It completely wrecks the network's learning signal. It causes massive gradient noise, totally unstable training. But modern models fix this with a lowest probability drop policy. Basically, the router selectively discards the tokens it was least confident about sending to that expert in the first place. That way, it ensures the most important, high-confidence tokens are the ones that actually get the specialized treatment.
Now, to prevent these massive traffic jams from happening in the first place, engineers use what's called a load balancing loss. Think of it as an auxiliary penalty added right during training. Without it, you get this thing called representation collapse. It's basically a rich gets richer effect. Watch what happens. One expert gets a few tokens, updates its weights, gets slightly better at its job, so the router sends it even more tokens. Pretty soon, one single overachieving expert is doing literally all the work while the rest of the network just sits there stagnating. So this load balancing loss acts like a tax on the router for being lazy. It actively forces the router to distribute tokens more evenly across the whole ensemble.
Moving right along to Section 5, Scaling to the Frontier, Ultra-Sparse Architectures. Let's look at Kimi-K2. It is a prime example of a frontier-scale MoE model. It boasts an absolutely staggering 1.04 trillion parameters. Honestly, trying to run a dense network with 1 trillion parameters would be economically disastrous for any company trying to serve it to real users. But remember, because it's an MoE, it is definitely not activating all of those parameters at once. In fact, Kimi-K2 operates with an extreme sparsity ratio of 48. Out of 384 total experts available in the layer, only 8, yes, just 8 are activated per token. This keeps the active compute incredibly low, especially when you compare it to the model's massive reservoir of knowledge. However, as you might guess, pushing sparsity this high introduces some serious stability challenges. Highly specialized experts can trigger these massive activation spikes when they suddenly see their favorite type of data. And that is exactly why Kimi-K2 relies on clever innovations like mute and clip. It's a specialized optimizer mechanism that aggressively clips these exploding attention logits. It basically slaps a speed limit on those spikes to keep the whole training process from just derailing.
Let's move to and see how this builds into an entirely new routing paradigm. To really solve those load balancing issues we were just talking about, researchers recently introduced expert choice routing. Standard routing is token-centric, right? Tokens basically line up like patients at a hospital, all demanding to see the exact same top doctor. Unsurprisingly, this causes massive traffic jams, while expert choice routing flips the script completely. Instead of the tokens lining up for a doctor, the doctors scan the waiting room and actively pull in the exact patients they are best equipped to treat, right up to their personal capacity limit. It's brilliant. It guarantees perfectly balanced workloads across all the hardware and literally eliminates drop tokens.
And finally, Section 6, the future of sparse AI, beyond the feed-forward layer. So traditionally, MoE was safely confined to the feed-forward, or MLP layers of a transformer. But now, it's breaking out into the rest of the architecture. We're now seeing mixture of attention, or MoA, where the attention heads themselves are routed to specific experts. This is huge because it allows the model to dynamically separate tasks, like, say, using one expert just for local grammar tracking and a completely different expert for long-context factual retrieval. We are also seeing MoE integrated directly into vision encoders, like in the Kumo model, to process complex multimodal images way more efficiently. We're even seeing structural routing, where entire broad concepts are adaptively managed by dedicated subnetworks. The ultimate promise here is efficient specialization at absolute scale. MoE is no longer just some clever mathematical trick to save compute costs. It's fundamentally transforming neural networks from these monolithic black boxes into hierarchically organized, multimodal, and highly adaptive ecosystems. And for developers, researchers, and just everyday users, this matters immensely. It means the future of AI isn't just about stubbornly building bigger, more expensive monolithic brains. It's about building smarter, dynamically routing ecosystems that can actually run efficiently on the hardware we have.
Now, what's really interesting about this slide is the profound question it raises for the future. We've watched sparsity ratios jump from 4 to 8 and now all the way up to 48, with hundreds of distinct experts dynamically specializing across both text and visual inputs. But as we transition fully into these highly complex, dynamic routing ecosystems, how far can we actually push extreme sparsity before the sheer communication overhead between the GPUs and just the overall infrastructure complexity completely eclipse the compute savings we get from all those sleeping parameters? That right there is the absolute frontier of AI scaling, and it's exactly what the top researchers in the world are racing to solve right now. Thanks so much for joining me on this explainer. Keep learning, and I'll catch you in the next one.